Researchers have taken a journey into the depths of space as astronomers continue to unlock the secrets of the universe. Groundbreaking analysis of an exoplanet located over 600 light years away is challenging our understanding of planetary physics. From its atmospheric makeup to its rotation patterns, scientists have been able to uncover fascinating new insights into this mysterious world. Well, joining us now to delve deeper into the world of Kelt 9b is PhD candidate from USQ, NATALIEA LOWSON. NATALIEA, welcome. Can you describe the methods used to analyse Kelt 9b and the significance of what you found?
We analysed Kelt 9b using what is known as a high-resolution spectroscopy technique, which is a bit of a mouthful, but essentially what it means is we look at the spectral lines of this planet as it is orbiting in front of its host star in very high precision. And from this, we are able to see the atmosphere of this planet and be able to detect if there's any molecules present. But we can also look at what is known as the photometry, or the amount of light that is being blocked by the star as the planet is orbiting in front of the star. And this can tell us a lot of different things about how big the planet is, as well as what this paper found, potentially interesting orbital trajectories.
Well, so what are some of the challenges that are involved in studying exoplanets like Kelt 9b, and how did you overcome those?
Fortunately for us, Kelt 9b is actually one of the best planets that you can observe. You mentioned that it is over 600 light years away, but it is also ridiculously close to its host star. And we call these type of planets ultra short period planets. But with Kelt 9b, it is also Jupiter-sized, making it an ultra short hot Jupiter. And we don't have any of these in our solar system. The closest planet we have to our sun is Mercury, and it's smaller than Earth for comparison. So we find these planets very fascinating, and we're not quite sure why they're there. There's been a lot of studies into this, and it's something we never thought was possible until we started looking at planets beyond our solar system. And so to have a very big planet very close to its star, for Kelt 9b, the orbit around its star is about 36 hours. So that's a year on Kelt 9b, 36 hours, which is insane. We're able to get a lot. So that's actually what made Kelt 9b such a great planet to look at with such a small telescope, was that it's very big. It's also ridiculously hot. It's over 3,700 degrees Celsius. So it was easy to detect using a 1.5 meter telescope, but easy with a grain of salt.
Yeah, easy when you know what you're doing.
Yeah.
So what are the implications of those findings in terms of the search for potentially, because obviously no one's living there, but other habitable exoplanets?
With this type of planet, what is great about it is, since we were able to find it using such a small telescope in comparison to what we normally need for these type of observations, it means that for being able to look at potentially other ultra-hot Jupiters in the future, we can do that using smaller telescopes, which is more easily accessible. And it just helps us understand more about planet demographics in general. And the more data you have, the better understanding you have of how everything works. So it was really fun getting to work on this project, and also being able to detect molecules in its atmosphere with such a small telescope.
So yeah, using the small telescope kind of doesn't make sense to someone who doesn't look through telescopes at planets at night. But how are you able to do it with such a small one when you think that you must be having to use massive ones to be able to detect something like Kelt 9b?
Yeah, well, the reason that we were able to achieve this is because although the aperture of the telescope itself is small, it's actually attached to what we call as a spectrograph, which has quite a big resolution and good enough precision to be able to determine or detect Jupiter-sized planets like Kelt 9b. So it's really having this spectrograph attached to this telescope that was the key player in us being able to detect this. So not all small telescopes, unfortunately, have the ability to be able to detect this kind of research.
So does that form part of research going forward, and how do you see the field of exoplanet research evolving in the coming years with those questions that still need to be answered?
I am very excited for where atmospheres is going to go with planets. That is what I work on with my PhD, and we don't have a lot of atmosphere data at the moment. And what we do have is for big planets like Kelt 9b. So I'm very excited to see the field move forward into understanding more about smaller planets and being able to see like what is a typical atmosphere for a planet. I mean, with Kelt 9b, what was very interesting from our research as well, aside from it being detected by a small telescope, was we potentially found that it might have a tail, which was giving it a weird light curve, back to that photometry I was talking about of the amount that a planet blocks light from a star. And if true, it could potentially show us more about what happens with planets when they're very, very close to their host stars in terms of atmospheres being evaporated, because that's what we think is happening in this situation, is that because it's so close to its host star, the atmosphere is actually being eroded away.